Okay, guys, this is example 7. This one's a little more complex. It's easy, but it's more complex in a way. It's going to be a simply supported beam. Reactions are known in the beginning. Okay, we don't know what they are. With a triangular shaped distributed load. The peak at the top of the triangular distributed load is 50 newtons per meter. The total beam's length is 0.6 meters. So how do we know what the reactions are? We can go down to the bottom here. You have to convert that triangular distributed load to a concentrated load, and you do that by taking the area of that triangle, so base times height over 2. The base is 0.6 meters. The height is 500 newtons per meter divided by 2. This equivalent triangular distributed load is equivalent to a concentrated load of 150 newtons acting directly in the middle, right? That's one force. So from inspection, if I have a one single 150 Newton force acting in the middle, and it's equally supported, each reaction must be 75 newtons. That's how I get those values right there. Okay, so let's do this the original way, and then we're going to use the formulas in the textbook and the handout as well. So if I had to do the shear diagram for this, I'm going to shoot up 75, right? 75 right there. Now, what do? This is a distributed load. So, and it's already first order, right? So just the curve itself is a first order line. All the other stuff was concentrated loads. Those are zero order. So the first line I draw, if this is first order, straight line, it has to be second order. Well, I know that this is 75, and I know that on the bottom, the back end, in order to close this up, this is going to have to be 75 or negative 75, right? So this one has to be second order that goes from here to here, from this point to this point. Well, in the middle, it's going to look like this. It's going to be second order to here, like a parabola, and then it's going to go like this to there. Okay, that's my shear diagram. So in other words, this shape right here, if I were to square this off, this is 1/2 of a parabola. Okay? So that's my shear diagram. It goes up, and you just have to know by looking at this triangle that it draws to that, and the formula sheet in the back of the book will tell you that. All right, just so you know, the sheet I'm talking about, it's this example on the blue page. It's this example right here. You can see they give you the shape, parabolic curve, and it's also in Appendix H in your textbook, page 504, case 3. Okay, same thing. Right? So you have two places to look for it. Now doing the moment diagram here, remember, any point along this curve here is going to be the area of the curve above it. So as in all things, they're going to start at 0. So if this is first order, second order, then the trick is, what is the area of this region? That's region 1. Let's call this region 2. If you look in your textbook, on the inside front cover, and knowing that that's a parabola, you'll see this second degree parabola shape. And you'll see that the area of that little wedge is 1/3 the base times the height, right? So it's telling you that for a parabola, here's a box, a square. It's telling you that the area this is, and this is the base, and that's the height, is equal to 1/3 base times height. Well, if that's 1/3 of the base times height, to make the whole thing, this area has to be what? 2/3 the base times the height, right? Add that together, you get the area of a rectangle, which is what? Just base times height. So, you know, this shaded part, which is going to be this part, this is 2/3 base times height, okay? So that's the area there. So if I wanted the moment value here, the moment value here has to be equal to what? A1 or 2/3 base times height, and that's equal to, let's do it over here. A1 is equal to 2/3 base times height, and that gives us, excuse me, 2/3 0.3, right? Because the base, this piece here is 0.3, because that's 0.6, 0.3, and the height is 75. So therefore, A1 is equal to 15. And because this is symmetrical, A2 is also going to be equal to 15. So, I'm sorry about that, guys. This is going to be A2, okay? So this is going to go to 15 right there. The question is, how does it get there, right? So this is a half a parabola. These curves are second order. That means the next curves down have to be third order. So I'm going to go a third order curve. And it's not really important how you draw it. It's just that you tell me that it's a third order curve. It's a cubic curve. Right there. But that's going to be my M max value. Pretty simple to do the traditional way. Now let's use the equations. Actually, when I look in the textbook, I don't like how they did a couple of them. I prefer to use this one. This one's better, but let's use the textbook because it's easier. And the corrections I'd ask you to make in the textbook, this one is not very good in the sense that it gives you this in terms of W. We don't know W right there. We know the peak value, which is W0, right? So if you can, in your book, change this first one from R equals V, cross that out, and put R or V, the reactions, or the shear at the ends, is equal to 1/4 the length times the peak value, W0. And that's equal to the reactions A and reaction B. So 1/4 L W0. When you get to the M max, which is that value right there, right? M max at center, that value right there, this WL6, not really useful for us because it's implying you know a W in the middle there. We don't, we only know the peak value. So replace that M max with L squared W0 divided by 4, right? L squared W0 divided by 4. And what I just told you to do is already present. It's already present on this. So I'm sorry, W squared, yeah, that's right. L squared W0, I'm sorry, that's not a 4, that should be a 12. My bad. That's a 12, and that 12 is already present right here. That's the M max value, that's what we're going for, right? So replace in your book the 1/4 LW0 for the reaction, and M max should be L squared W0 divided by 12. Now let's see if using these equations, if we get the same answer, okay? So here, in this problem, W0 is equal to what? 500 newtons per meter. L is equal to 0.6 meters. We said that RA is equal to RB, and that's simply equal to 1/4 L times W0, which is going to be 1/4 times 0.6 meters times the 500 Newton meters. Here we get a value of 75 newtons, okay? So that checks out, right? That gives us what we did traditionally, and we saw from inspection, it gives us the same thing. Let's do the M max value. L squared W0 divided by 12. You get 0.60 squared. W0 is 500. And this is 12, and we get a value of 15 Newton meters, which is the same as we got right there. So once again, if you see this, just like the previous example, example 6, if you see this loading pattern and it jives with one of the examples in the back of the textbook or the handout, just go straight to the equations and you wouldn't have had to do any of this. This is a lot easier, right, than doing all this and having to know the area of a parabola. Anyway, I just want to show you that there's more than one way to skin the cat. Got a few more examples, and we'll do those too, okay? Bye.